This is problem 19-29. A 25-pound box A slides down a ramp at an angle of theta equal to 25 degrees and strikes a 10-pound box B, which is attached to a spring of stiffness K equal to 10 pounds per inch. On impact, the two boxes become hooked and slide as a single unit on the rough 0.4 friction coefficient surface. If box A starts from rest with D equal to 20 feet, determine A, the velocity of the boxes immediately after impact, B, the maximum compression in the spring during the resulting motion, and C, the acceleration of the boxes at the instant of maximum compression. Okay, this problem has at least one thing in it that I find somewhat annoying, and I only know that this mathematical quirk is the way it is because of how this book does other problems. So I want to point out the one little issue that goes on in this problem. Let's go to the whiteboard and I'll highlight what I mean. Okay, so if we look at the diagram that the book gave us, it gave us a box, gave us another box, it gave us a spring, and it told us that box A starts from rest at 20 feet. And then box B, it just kind of says that box B is there. Okay, so that means that we technically don't know where box B is. Now, we could say that box B is starting at some location. Maybe we talk about the center of mass being at location 0. Okay, fine. But the thing is that there is a spring here. Now, they just tell us the spring coefficient. But again, they don't tell us if this box is starting with the spring uncompressed, which means the weight of the box would push down on the spring, cause the box to move. They don't tell us that the box is at some compressed or extended position. And so we have to make an assumption. We have to make an assumption that this box has started at some position for the spring where the spring is compressed, but box B is not moving. Okay, so I mean, they technically don't even tell us that box B is at rest. So this is a slightly annoying setup for an engineering problem, a dynamics problem. So that's why I want to highlight this and show you what assumptions you need to make. Okay, so to kind of re-say all the stuff I said, but in a nutshell version. Box B is compressing the spring and not moving. We need to find out where that box is. So if box B is not moving, then we could do a sum of the forces, and I'll call this in the x direction, so we'll say this is the x direction. And so sum of the forces will equal ma, and we're going to say that there is no acceleration. So ma is going to be 0. So what are the sum of these forces? Well, it's going to be the weight of the box sine 25 degrees, because the weight is straight down, but the x direction is parallel to the ramp, and then minus the force of the spring, which they give us that the stiffness is 10 pounds per inch, but we don't know how far. And that is what we want to know. So it'll be the stiffness times some delta, and then again, reiterating equal to 0. So if we solve for delta, this equals 0.4226 inches, and that equals 0.035 feet. Okay, so that's where box B starts. From this, I guess if you consider this marking being the 0 position, and then the box moves 0.035 feet to the right. All right, that is the starting position for box B. So that means distance D is 20 feet, like they say. But box B's position is already at this compressed position. So this is not adding the 0.035 feet to distance D. It's not making it 20.035 feet. We know box B is sitting and waiting to get hit by A. And the problem tells us that box A is going to go 20 feet. What's important is that we know that this spring is already compressed 0.035 feet. Because when box A hits, the spring is going to want to compress more, and we need to know that the spring is not starting in an uncompressed state. It is already slightly compressed. Here's the last thing though, and I didn't mention this as I was setting up the equation. We are assuming a static equilibrium, but they give us a friction. They give us a friction of 0.4, but they only give us a kinetic coefficient of friction. They don't give us a static, and box B is not moving. Therefore, we can't include the friction in the calculation. It doesn't make sense. I find it kind of annoying. I wish they would have just given us a static coefficient of friction. It would have been more realistic. But it also would have made the problem a little more complicated. And at this stage, I have a feeling that knowing how to calculate the static coefficient of friction in the sum of force equation is within your capabilities, definitely. I can kind of understand why they didn't want to add in that complication, but I also think it risks ruining the intuition that you can build from these problems. So we have to leave it out. We cannot put the friction in this static equilibrium equation, which I actually find a little bit annoying. Okay, so because there's going to be a kinetic friction but no static friction, that honestly does not make any sense. Okay, so understand that we are intentionally leaving out a term to find where this box B is going to be during static equilibrium, because they don't give us the information necessary to include the friction term. All right, all of that setup now aside, let's actually work on the problem. So the first thing we're going to do is use the work energy method to determine how fast box A is moving just before it strikes box B. We need to know the friction that box A is experiencing as it is sliding down, so that way we can calculate the work of the friction. You know, that friction that wasn't there for box B, but now is there for box A. Weird, but okay, the problem does tell us the kinetic coefficient, so we need to use that. All right, so let's find the normal force for box A. So some of the forces for A in basically the vertical direction is going to be the normal force minus 25 cosine 25 degrees equal to 0. So that means that the normal force is equal to 22.658 pounds. Okay, that means that the friction for box A is 0.4 times the normal force, which equals 9.063 pounds. Okay, now we know the friction acting on box A. Then we can calculate the work that is being done on box A by the friction and also by the gravity or the weight. And we know from the problem that box A starts from rest. So the initial kinetic energy, that's supposed to be initial, is going to be 0, okay, plus the work that's going to be calculated for the friction and the gravity, and then that equals the final kinetic energy, and that will give us the velocity of the boxes when box A, or the velocity of box A when it hits box B. Okay, and you could consider the, well, no, yeah, this is just for box A. So let's go ahead and do that. So we have 0 for the initial kinetic energy, plus the weight and the component in the direction of motion, so sine 25 degrees, times the 20-foot distance. Okay, and then also the friction, so minus the friction, 9.063 times the 20-foot distance. Those are the two works. And then this is equal to the final kinetic energy of 1/2 the mass, which is 25 divided by 32.2, and then the velocity of A squared. Okay, so the velocity of A ends up equaling 8.798 feet per second. All right, so now we have set up to find out part A. What is the velocity of the boxes immediately after impact? So now we will use the linear momentum equation. All right, the setup for that is going to be that that box A is going to have a mass of 25 pounds divided by 32.2 times the velocity, 8.798 feet per second. Okay, so that's the momentum of the first box, box A. The momentum of the second box, even though it's 0, I'll just write it out, is the weight divided by the acceleration due to gravity times the velocity of 0. So that's all 1 unit. Okay, there is going to be a collision where they're going to be connected to each other. So no impulse, no external impulse. And then collectively, they're going to be a mass of 35 pounds divided by the acceleration due to gravity. And that's going to be times the velocity of the boxes combined. So we can solve for the velocity of the boxes combined is equal to 6.28 feet per second. Right, that's part A. Part B is the maximum compression in the spring during the resulting motion. All right, well, we can use the work energy equation again for this. So now there is a velocity that the box AB system is going to have. That is going to give us an initial kinetic energy. Then there's going to be work that's going to be done. There's going to be the work of friction and the work of the weight. And then on the back end, on the right-hand side of the equal sign, there's going to be some final kinetic energy. And we're going to have to deal also with the potential energy. Okay, so technically you could, again, think of the work done by the weight or the potential energy of the weight to be the same thing. Okay, so we can do this equation in slightly two different versions. I'm running a little low on space. Let me move things around a bit here. And we need to find the new friction. So why do we need to find the new friction? Because the two objects are combined together and they're going to have a new normal force. So the new normal force is going to be 35 pounds cosine 25 degrees still, and that's going to equal 31.721 pounds. So this is the new normal force of the combined boxes. So therefore the new friction is going to be 0.4 times that normal force, which is 12.688 pounds. All right, that's our new friction force. Now our work energy equation is going to be the initial kinetic energy plus the potential energy plus the work equal to the final kinetic energy plus the final potential energy. This is the spring, okay? So we will have 1/2 times the mass, 35 divided by acceleration due to gravity, and then the velocity, so 6.284 squared. And that's what we found last time. All right, and then we are going to have the initial potential energy of the spring. Remember that box B already started with the spring a little bit compressed. So we'll have the spring constant times the distance, plus this is, sorry, 1/2, okay, times the 0.035 squared, feet squared, okay? And then we're going to have the work done by the friction, and that's going to be negative 12.688 pounds times however far this system is going to travel to get to maximum compression. And remember, that's the point for maximum compression. Okay, so now we get to the right-hand side of the equal sign. Our final kinetic energy is going to be 0 because the two boxes are going to compress the spring to full compression, not the stop, like the spring won't be able to squish anymore because all of the coils have knocked into each other. The spring is capable of compressing more physically. It's just that the box is not going to fully compress the spring. This is the maximum compression due to forces, not the maximum compression due to the spring fully collapsing. Please understand the difference. So since the boxes are going to compress the spring until the spring has overcome all of the energy of the two boxes, the boxes and the spring will come to a stop for just a brief instant, meaning the final kinetic energy at that moment of full compression, or not full compression, maximum compression. Understand the difference between full compression and maximum compression. The velocity is going to be zero. So therefore the final kinetic energy is zero. All right. Now that means that we have some potential energies to deal with. Well, that means that we're going to have the stiffness of the spring and then times the initial compression due to box B resting on the spring plus the distance that's already traveled squared. Oh, and don't forget the 1/2. Okay, and then we're also going to have the potential energy of gravity. So that's going to be below the starting point, and that's going to be the mass, the weight, because it's gravity, and then times however far traveled sine 25 degrees. Okay, that one might not be so obvious. Take some time to think about that. But you do know what you need to know in order to make sense of this. The distance traveled and the gravity. Okay, so this is the vertical distance. All right, we don't know that distance, and this is the potential energy. It's negative because we're below a certain point, but we still have to, we're below the reference point, but we still have to take this into consideration. If we solve for x, and now it's quite a bit of algebra, if you solve for x, you will get 0.581 feet. All right. And so the compression of the spring is going to be that new distance plus the initial compression. So the delta max is the 0.581 plus the 0.352, which is going to equal 0.616 feet. That is the full compression of the spring from the zero compression point, where B had started the compression already, and where box A running into box B compressed the spring even more. Okay, now for part C. Part C is not hard, but all we need is, they're asking that we find the acceleration of the boxes at the instant of maximum compression. We can just use the sum of forces for this particular part. I need a new page. Okay, so sum of the forces is going to be equal to the spring's compression, the force of the compression of the spring. That's 10 times the full compression distance, 616. Okay, and then minus 35 pounds, sine 25 degrees. Okay, minus 12.688, that's the friction. And then that's going to be equal to the mass, 35 times the acceleration due to gravity, and then the acceleration. There we go. Right, we just solved for A. So the acceleration is equal to 42.7 feet per second squared.